Hi, so today I'm going to go over all of the elementary particles that you need to know, and I'm going to um, cover all of that and see if we can go all of 7.3, but may or may not need a part 2. So first off, what is an elementary particle? Let's define that first. So the number one thing that differentiates an elementary particle from any other particle is that elementary particles have no internal structure. They can't be broken down into anything smaller. There's one more classification that I'm going to introduce, and that's an antiparticle. So an antiparticle is going to be a particle that has the exact same mass and lifetime as their particle counterpart, but they have opposite values of charge. So same mass and lifetime and opposite charge. And so with those two classifications done, I'm going to move on to our first elementary particle, which is quarks. So first off, quarks, they're a type of elementary particle, and they consist of different types of quarks. So for example, up, down, strange, charm, top, and bottom. And right now it just looks like I've written a bunch of words, but these are all actually types of quarks. So we have up quarks, down quarks, strange quarks, charm quarks, top quarks, and bottom quarks. And as I mentioned earlier with those antiparticles, we also have antiquarks. And so all of these particles will have an antiparticle counterpart. So quarks either have -1/3 or 2/3 charge, depending on which type of quark they are. And that obviously is going to mean that antiquarks will either have 1/3 or -2/3 charge. One thing to keep note is that there is this other property of elementary particles called strangeness. And this is a pretty interesting property that I'll go into later. But strange quarks, they're going to have a strangeness -1, and anti-strange quarks are going to have a strangeness of +1. So now with quarks, there are some particles you can make out of them, and those are going to be called hadrons. Hadrons are basically particles that are made up of quarks, and they're held together by the strong force. And under hadron, you have two types of hadrons. Number one, you have mesons. So these are made up of a quark and antiquark. And then you also have baryons. You also have, I wrote that B weirdly. You also have baryons. And these are going to either be made of 3 quarks or 3 antiquarks. And so there's 2 quark-related things that I want to add on over here. And one of that is quark confinement. So quark confinement is this observation that you can never isolate a single free quark. And so the reason for explaining this is that the strong nuclear force between quarks stays constant no matter what the distance between them is. And so let's say we have a baryon, and we're trying to pull this quark away from the other quarks. The strong nuclear force is always constant, and as the quark is separated, if we're trying to pull it apart, the energy transferred gets bigger and bigger. So let's put this in an equation that might be easier to understand. Work done is equal to Fx. So our F is going to be constant because our strong nuclear force is constant, but X is increasing, which means the energy is increasing. And so what happens is that the energy required to separate this quark from the other two quarks is much greater than the energy required to produce a meson. So what happens instead is that when we try to pull this quark away from the others, instead of isolating it, what just happens is we create a meson. One more thing I'm going to bring up over here is deep inelastic scattering. And so deep inelastic scattering is the experimental evidence for quarks. And so what was done is that energetic electrons were fired at protons. And so what was noticed is that at energies greater than 15 GeV, there would appear to be points of deflection. And so those points of deflections would depend on what that particle was. So in protons, those are made up of 3 quarks, so they're a baryon. And so it would be noticed that there were actually 3 points of deflection, which actually indicated that there were 3 smaller particles that made up this proton. And so this experiment was an experiment that helped determine that quarks are point charges. Now I'm going to move on to the next elementary particle, leptons. So leptons are particles that do not experience the strong force. These consist of electrons that we're very familiar with, muons, taus, and then you also have neutrinos for these 3. So you're going to have electron neutrinos, muon neutrinos, and tau neutrinos. So, let me write this in anyways. Electron neutrinos, muon neutrinos, and I'm going to need more space here. And tau neutrinos. So those are some leptons. And so one thing to note is that electrons, muons, and taus, they have charge. But these neutrinos, they're actually so small that they basically have no charge associated with them. And so all these leptons are going to have a lepton number of 1, and antileptons, just as you have antiquarks, you're also going to have antileptons. They're all going to have a lepton number of -1. And so this idea of lepton number, that's going to be associated with the type of elementary particle. And quarks will also have that kind of number associated with it, although it's not going to be called a lepton number, it's going to be called a baryon number. And each quark individually will have a baryon number of 1/3. But leptons, on the other hand, each individual lepton will have a lepton number of 1. Now I'm going to go over fundamental forces and exchange particles. So when I was talking about quark confinement over here, I was mentioning this idea of the strong nuclear force. And so the strong force is actually a type of fundamental force. So let's start off with that one. We have the strong force. It acts primarily on quarks. And the exchange particle is basically, the particle that ensures this force. And so for the strong force, that's actually going to be the gluon. Let me make this a little bit easier. So force acts on, and exchange particle. Another fundamental force is going to be the electromagnetic force, and this is something you guys are probably going to be aware of already. So it acts on charge, and its exchange particle is going to be the photon. Our third fundamental force is going to be the weak force. Just as the name suggests, the strong force has a much higher relative strength than the weak force. The weak force is quite weaker, so that's where the names can help a little bit. The weak force acts on quarks and leptons. And the exchange particles are going to be bosons. So it's going to be these particles. And lastly, we have gravity, acts on masses. And so the exchange particle is going to be the graviton. So these exchange particles, you don't need to know too much in depth on how they work, but a very, very brief way of explaining is that they carry the force and they go back and forth between the particles that they act on. So let's move on to the next one, particle interactions. So in particle interactions, there's 3 things that need to be conserved: charge, baryon number, and lepton number. There's an additional property that doesn't quite need to be conserved, but it does in some sense, and that's going to be strangeness. And the reason why I'm grouping this separately is that the charge, baryon number, and lepton number, they have to be conserved perfectly. But strangeness, there can be a difference in strangeness of up to 1. So even when you have a difference of strangeness in 1, interaction can still take place. So the last thing I'm going to go over is pair production and annihilation. So in pair production and annihilation, it basically indicates that when a particle and an antiparticle meet, the 2 particles annihilate to form energy in the form of 2 fast-moving protons. And so the energy produced is equivalent to the sum of the mass energy. So it can be written like this. And so basically what this is saying is that at the very beginning, the kinetic energy of the particle, and the kinetic energy of the antiparticle plus the energy that is a result of their mass is the total energy at the end. So it's the initial energy, and then these two indicate energy at the end in a different form. And 2 mc squared, that's going to be rest energy mass. Right, so over here, I've gone through all the things you need to know about fundamental particles. In unit 7.3, there's still a couple more things that you need to know, like Feynman diagrams, but we'll make a separate video on that later, going more in depth. But that's it for fundamental particles.